try to fill them.
All right. Go. You wanna oh, none from. All good?
It's included. Yeah, it's included. I'm going to just use it, right? So we're just driving for hours. Yeah. Hey man, it's driving for many hours.
Okay, let's get started. We're a little behind. So that's my name there on the bottom. Nice long German name. My name is Michael Schloh von Benewitz, and my company is Europa Lab Networks. We do a lot of telecommunication, things like web hosting, email gray listing, remote backups, distributed storage. So what am I doing here with Internet of Things? And well, because it's an Internet of Things day, isn't it? We have had the last three speakers, Michael Brown, Aaron, they both did a great job. So we'll be concentrating a little more on sensors and the data that the sensors send to the computing nodes. So that's a telemetry stream. And we'll have some cool demonstrations of mostly Bluetooth, because I don't have any Zigbee devices, but I do have a pretty cool Bluetooth device here, a handheld Node Plus from a manufacturer called Variable. And those folks asked me to offer you here, you can write your email number there, and you'll get an email from them with some marketing information, and you get electronic copy of the slide deck as well. So I'll put that up here for later on, whoever wants information from Variable, the manufacturer, and slide deck. You can see the URL as well, which is where this is all hosted. It's online right now, so if you have a device and you're courageous enough to stack without fielding any attacks, then you can actually follow along these slides. So let's get started in this hour. We'll be covering a few different topics, and there they are. Try to go faster since we are behind. So we'll cover some basic IoT definitions and figure out what sensors are, how they operate and relate to computing nodes, telemetry, what that is. I think we'll skip over most of the marketing because we've kind of had that in the previous presentations. We'll talk about MQTT mostly, the message queue telemetry transport, which is a protocol which quite a lot of IoT sensors and computing nodes use when they're transmitting sensor data. We don't have any CoAP or other RESTful HTTP type of demonstrations, but we can consider what that is, how that's different from MQTT. And then if we can get to these 3 demonstrations, I'm not sure if we'll have time for that, but we will do an in-depth demonstration of attacking a Bluetooth, the Bluetooth transmission of a handheld sensor with well, we'll get to that later. A lot of nice Bluetooth, which is challenging, so I think that's the most interesting for us. And since we are going to be attacking Bluetooth live, and I'll just be using the default tools for that, so I'm not hand coding, to only pay attention to certain MAC addresses and so on, you might want to rename your Bluetooth device identifiers. That's the MAC address for for your devices and the associated name for that. So if you have an Apple device, for example, almost guaranteed that the default name associated with your identifier is your real name. So I assume this is being broadcast or at least videotaped, which is kind of strange at this conference, but you might want to either change those names or turn off Bluetooth, airplane mode, or if you think it'll help, then you could put it into non-discoverable mode. We'll see if that helps later. So here's kind of the bird's eye view of Internet of Things. There's plenty of sensors involved and telemetry streams from everything big like power plants to smaller things. I'm going to try to get my laser pointer, to smaller things like wearables, wristwatches, and so on. And good to have a bird's eye view sometimes to help us maintain perspective. So there's a lot of different protocols as well. We have IP protocols like Wi-Fi and Bluetooth, Zigbee, the things that we've talked about in the other presentations. I think let's move on to give more time to the demonstrations. Here's something else, kind of for a more marketing-centric perspective, product types and industry segments and who's using what, where the government is buying and what other players are, and big players are trying to produce in the industry. And here's kind of the slope of devices, which are bottom 2018, so that's coming up pretty soon. And personal computers, desktops, and so on is a pretty flat curve. So that's not going anywhere, but it's not going away either. And then above that, we have the mobile crowd, the smartphones and so on, tablets above that. But what we see really taking off is the things up above, the Internet of Things, wearables, smart TVs, and these kind of consumables. So that's the marketing case for getting involved with all this. And this is kind of the history which we've seen regarding software and prototype and protocols through the years. Typical consumer things like HTTP traffic from web applications. I think, yeah, we've had this as well. I think Aaron talked about this. So this was actually pretty good, and this is just repetition. So, for example, Gartner says that 26 billion IoT devices will be on the market by 2020, and that's quite a lot. Here's some examples, things that you might have in your own home or your company or whatever. There's a Nest. These are all, so this is a beacon. It's a BLE, Bluetooth beacon for proximity geolocation. We've got a lot of sensors, altitude and pitch and so on, which most drones have. Here, this is cool. I like this one a lot because this is just the casing. The thing inside is the circuit board there. This is a smart traffic lamp. Either a traffic lamp or a street light. I actually can't remember, but it's one of those. And would be a lot of fun to manipulate that, I think, on the street where I live. So if it's Bluetooth, I'll try it out. Now, if we try to imagine how telemetry works and how sensors attach to their computing nodes, which concentrate the data, store it, or forward it to other computing nodes, it kind of works like a human body, right? With your head up here, the brain, that's a CPU. And then you have your sensory organs, touch, smell, taste, hearing, and so on. That's not, I'm trying to get tangled up here. That's kind of a good way to approach it. That's telemetry, and this is the way that machines look at these connections. So instead of a human body here, what we have is basically the CPU in the middle. This is a sensor router. There's some kind of processing equipment inside there connected to the sensors at the bottom down below. Sorry, I'm kind of... So there are the sensors down below. And then what we can have is basically forwarding the information onward to as many different networks as we want over different transports like GSM, if we have a weather balloon, for example, or Ethernet, cabled, Wi-Fi, whatever else. Those are the two models, kind of the biological model and the end-to-end machine model. Speaking of biology, humans do play a role in the Internet of Things, and there's a lot of sensors. I actually have this wristwatch on me right now. Maybe I can do this cheese and things. There it is. So there's a wristwatch, but it's upside down. And that's not going to work too well. What I want to, that's not what I want to show. What I want to show is the sensors that come on here by default. So there they are, and I'm not sure if you can see that too well. Okay. So there's a heart rate monitor, there's a step monitor, there's a sports something or other, which probably combines the things, and then sleep. Not sure what sleep does. I guess it depends on the movements that you do in your sleep. Haven't tried that one out. There's another wearable device, which is a headset. And what kind of sensor could be attached to a headset? It's actually a very creepy idea. I don't know if anybody owns a pair of these, but they measure your pulse just by putting them on your ear. So I'm not sure how it works. I don't think I want to have one of those on, but it could be sending these your pulse signals over a Bluetooth connection to your smartphone or something like that, for example, and that would be telemetry, with the smartphone acting as a router or concentrator. So now that we're speaking of biology and wearables, little pop quiz. Has anybody heard of this? A band? Anybody want to care to take a guess, a wild guess at what a band is? A B-A-N? Maybe. It's the body area network. It's the body area network, and this is actually, I know the first time I saw that, I thought it was a joke. And then I read the bottom, the footnotes. There was some small text about FCC regulations, and so FCC actually regulates the frequencies that you can use for a band. So it's not a joke. It's a very serious and standardized thing. So that's what's being used for sensory data on a body area network. That's creepy. So anyway, so we have more than little things involved in sensory data in the IoT. There's a lot of critical infrastructure which depends on sensors. Any of these things, for example, which we can imagine we want to protect and defend against as many attacks as possible. To pressure and temperature, for example, at power plants, we don't want things exploding. Or military geolocation, when we're kind of lobbing mortars in the military exercise, we don't want those landing in the wrong buildings outside of the exercise area. Aircraft altitudes would obviously could result in very bad destruction if they were forged or false. Water chemistry and treatment plants and so on. These are all dependent on IoT sensors and good telemetry, which is secure. Then there's a more legal question of researchers like we are and how we release our findings and reports once we find vulnerabilities, what it could mean to have a zero-day attacks published on any of these type of sensors like insulin pumps, EKG monitors, heart rate, electro pills, the medical doses that Aaron was talking about before. So the EFF has taken a look at this, but kind of not gotten into it too far. Every time they've been asked by reporters, they've kind of distanced themselves, not taking one side or the other. So it's kind of still up for debate how far researchers can go. And then going back to our diagram, we can take another look now and try to imagine where the sensors are in this diagram. We have things like temperature sensors or thermometers that are measuring forest fires or smoke. For example, what we had before with the street light. So we have things like that. Let's move on. And for a word definition of telemetry, now that we've covered IoT and sensors, we've got two definitions from NASA and from Wikipedia. NASA is a particularly long one. They're kind of more scientific and space-oriented, but they're saying that telemetry is the highly automated communications process by which measurements are made and other data collected at remote or inaccessible points and transmitted to receiving equipment for monitoring. And Wikipedia cuts it a little closer and says that a telemetric system consists of a sensor, a transmission path, and a display recording or control device. So that's kind of what I find interesting, because transmission path can be anything from Wi-Fi to Bluetooth or any kind of transport, wireless or cable transport. That's what you need to have a telemetric system. And the sensors, of course, things like pulse or altitude, anything that a sensor can measure. And then you have the control device, which is typically a computer processor, something with a CPU inside. So here are typical telemetry protocols. The first two are probably the most common, MQTT and COA, which have been specified quite clearly and are in widespread use. I've seen some things coming from universities, like trying to do things with raw TCP or with HTTP and REST, and then keeping the connection open by sending keep alive or something else. These are not in use by industry or people actually making the IoT nodes and sensors, because they typically are low energy devices, and HTTP is a thick protocol, which when you keep it open all the time really drains the batteries fast. And for a variety of reasons, XMPP is kind of the same way. You can add more protocols to that list, but the most two common are the ones at the top, MQTT and COA. So here's an example of how an MQTT connection is built. I would love to draw this, but if I unplug the monitor, should I try that? Okay, we'll take a risk. Did you see that? Okay, we'll take a risk. See if the monitor reconnects after I switch to this one. So I can. And signal itself. Get to that. Oh, it only worked on one side? Okay. Is that good enough? Oh, it's on both sides. Okay, cool. So then I can draw what looks like typical MQTT flow looks like this. So HackMiami. Let me spell that on purpose, by the way. I want to tilt that. Okay, so what we have, so MQTT is a publish subscribe protocol. It's a little different than others, and it's another reason that people use that in IoT. So you have typically your, let's do Let's put 3 actors up here. We have our broker. Make this big.
Make the background black.
That's it. Make a broker. We'll make this one the MQTT subscriber. And we'll say this one is the publisher, right? Publisher. So what happens then, this is kind of here, these are roles, this is kind of the server. These two are clients. I don't know if this is proper UML. Kind of forgotten my UML, but let's try another. Okay. So then we have the lifelines over here, and so the broker is always on as like a web server or SMTP server or something like that, and then the MQTT subscriber will say, I'm subscribing to the topic HackMiami. HM is the topic name. So, and nothing happens then. Then we have our publisher here. And this sends a message. Let's go back. Miami, and the message is session start or something like that. So then the broker, this guy here, that's going to send to the subscriber the message session started. Right? And if this guy here then sends another message, but from another topic, like, what's a competing conference that really sucks? I don't know, maybe DEF CON?
All right.
Okay, so then we say this is a different message. Sucky. Okay, so the broker does nothing because actually there is no subscriber for DEF CON. I mean, nobody wants DEF CON, right? So anyway, that's how MQTT works. It is a publish subscribe protocol. Now let's go back here. Okay, so moving on. This is kind of the programming side to it. You can kind of see this as JavaScript, but you can do this in C, C++, or anything else, or MQTT libraries for anything. And so this is an example of the subscriber. This is actually quite cool. If anybody likes to program JavaScript on the server side and uses Node.js, for example, there's a really good MQTT library for that. And with so few lines of code, what is this? Okay, not counting the comments, we have 1, 2, 3, 4, 5, 6 lines of code. You just wrote an MQTT program, right? And it's pretty easy to follow and easy to understand. So you just have the host name here. You're saying to connect to the broker, which is that. And this is basically, we have a demonstration for this, but I'll do it only if we have time to get to that. The next one is for the subscriber or for the publisher side, and it's basically the same. It's even easier actually. This one's in 4 lines. So it's just insanely easy. I think that's another reason people like MQTT. Co-op is a little bit harder to master. So if we get to the demonstration, then we can use a hub or LAN tap star like this to monitor the MQTT traffic flow between the publisher and the subscriber, or the publisher and the broker. This is what I was using in the hotel room before my LAN tap broke. So I'm not sure if that'll work. There's a few topologies common in IoT and which sensors use. And this can get involved because sensors sometimes can connect to themselves, like Michael Brown was talking about. Michael, I think Brown is his name. Some sensor technologies use Zigbee, for example, as a protocol transport, and Zigbee and Z-Wave are both able to mesh with other Zigbee devices out of the box. So that basically means that each device can do P2P. We have a tree topology, which is a little less common, but what's interesting about this one is you have two different master nodes, one there and one there. They're kind of central control masters, right? So this could be useful in some situations when you're trying to bridge things or making things redundant, where if one master goes down, only that portion of the network will stop functioning. The most common, well, here's the mesh network again, the thing that Zigbee does so well. The most common, of course, is a star configuration where you just have one master in the middle, and if that goes down, your whole network is dead. So, but it is quite easy to implement, and so that's what Bluetooth uses, for example, when you have a Bluetooth PicoNet, which looks like this. So this is what all Bluetooth networks look like. You either have one master and one slave. If you're pairing your headphones, your headset to your smartphone or some other device, that's what you're doing. Or you have several slaves and one master in the middle. And when you have this configuration, all the slaves need to be working on the same mode. So you either have Bluetooth 1 or Bluetooth 2, Bluetooth high speed, or Bluetooth low energy. They can't be on different modes. Here are some Bluetooth low energy applications. And this is why we're going to test Bluetooth in depth, because Bluetooth is kind of very prevalent in IoT and sensors. And so when you have things like beacons, it's almost always doing BLE, blood pressure monitors, all of this stuff. Unfortunately, so Bluetooth low energy is actually easy to crack, but it's very low power, can't send data very fast, so once you do crack it, you can't do very much with it, unless you're just interested in its identification. I don't have any, well, I do have this device. This is Bluetooth low energy. We can try monitoring that. The problem with the Samsung wearable devices, though, is that you need Samsung, they have a walled garden architecture for all of the software on any of these, so they will only speak to other Samsung devices, and that presents an additional challenge. You can still get into the wireless, the Bluetooth transmissions from all the sensors that are loaded on here, but it does present an additional challenge, so I don't think we can do that in a few minutes. This is what we're going to be using for our testing. Where is it? I have it over here somewhere. It's, I'll turn it on first, and then it makes a beep. Cool. And did you see the light? I mean, that's why you need to get one, right? So anyway, this is a very interesting device to test with, because both of the so without anything mounted on or screwed onto these sides, you can see these screws. It basically has in-house, it has a few sensors on there. It has at least a magnetometer and accelerometer. I think it has one more. Can't remember right now. I assume that there is some microcontroller on there. It could be a SoC, an ARM-based SoC, but it could be an AVM microcontroller as well, some kind of Arduino thing inside there, which processes all of the sensory data before it sends it out over a Bluetooth connection. And this is the button that I just pressed to turn it on. It's also what I use to scan barcodes, which we'll see in a minute. So you can screw on the side of this device, on both sides in fact, like a choice of devices. I'm not sure how many, probably about 10. There's things like Chroma, Luma, there's the measuring of light and colors of the light. This is useful for people painting houses or doing things with paint, I guess, graphic design and so on. There are altitude sensors. I have a thermometer and a barcode reader. There are a few other things that measure oxygen content, nitrogen, what's the other one? Carbon dioxide, carbon monoxide. So you have your choice, and yeah, it's pretty cool. So let's see. First things first. I can't remember if we're going to. Well, yeah. Before turning that on and starting to test, I need to explain that it's actually pretty difficult to attack Bluetooth compared with Wi-Fi for a few different reasons. You have your MAC address, like you see below, for each device, which is split into two parts. The part that is assigned to the manufacturer by a central number registry, and then you have the part that the manufacturer decides on their own and assigns to each device so that they're unique. The trouble is that when you're reading radio data from the radio landscape and you identify it as Bluetooth because it's a 2.4 to 2.5 gigahertz band, which is shared by Zigbee and Wi-Fi as well, but you can figure out that it's Bluetooth in a few different ways. You only get this LAP value. Most of the Bluetooth frames that you capture don't include the manufacturer portion. So you kind of have to wait for 10, 20, sometimes a few hundred frames before you catch one with the manufacturer portion glued onto there. And this is important for a few other things, namely, we'll get to that later, that's the next challenge presented to the person trying to attack Bluetooth, is that it's a channel hopping protocol. So it's not like your Wi-Fi typical channel that's always occupied by one device, and that device is only transmitting on that one channel. Bluetooth will actually switch channels on the fly, and it's a pseudo-random sequence, which is exchanged between the master and the slave at the pairing stage. So unless you are already decoding the frames at the pairing stage, which you very rarely are, you don't have all of this information. And then what you see is that you listen to one channel and you get a few frames and then nothing else, because the two devices have already moved on to a different channel. They've maybe switched and skipped over channel 2 and gone to channel 3. There's 79 channels, so you're dead in the water, because this happens as well very fast. This is a 1,600 times per second. So it's pretty hard to crack devices transmitting over Bluetooth. Here is the Bluetooth model. This kind of resembles the OSI 7-layer model. And the other thing is that you have your HCI, your host control interface, around this portion, which is a green portion. This is actually what your typical laptop can do. They can measure the HCI, drill into the HCI layer, and nothing below that. But what we need, if we're going to actually be measuring this channel hopping and making guesses about the clock rate and which channel the next one will be the correct one, we need to be measuring at the baseband, which is at the very bottom. So we can't use the chips that are actually in our smartphones and wristwatches and notebooks for attacking Bluetooth connections. They're useless for that. We can get some simple data like the manufacturer name and so on, but actually capturing the frames, we need something else for that. And to do that, I've brought another device here. Let's see if I can get Mr. Cheese again. I don't know why I'm doing this, because I think there's a slide showing this a lot better. So there's the antenna. So that thing, I'm going to plug that in pretty soon. That's a that's a Ubertooth device which can capture frames at the baseband layer. So another thing, we've already actually taken a look at the network architecture, which is a PicoNet, so star formation or star topology. And we know now that we have the LAP, the lower address portion, the upper address portion, and the non-significant address portion that make up the MAC address of each Bluetooth device. Then the thing that we really need to decode the frames individually are these three things at the bottom. The lower address part, the upper address part, which is not sent in every frame, and the internal clock sequence of each device, because we need to know when they're hopping to the next channel. And there are actually 2 clock values that each device has according to the standard. So this all gets quite hairy. I'm sorry. And here is there's a frequency hopping standard or algorithm, which is in the standard, which is called adaptive frequency hopping. And there's a map for that. And this can change as well according to a reconnect that is in the standard as well. So the folks who made this device, the Ubertooth 1, the original inventor of the hardware, Michael Osman, and the current software lead, who was around during the development of the hardware as well, but he's the guy doing all of the development right now. His name is Dominic Still. I have quite a lot of respect for those folks, because doing all of this as well as error correction and a bunch of other stuff that doesn't exist in hardware. So these are all the things that we take for granted when we're hacking Wi-Fi, right? Just put a Wi-Fi chip in monitor mode or an Ethernet cabled interface in promiscuous mode, and you get all this for free. And so what they've done is a lot of good work. And let's see how that works now. I think it's about time. Oh, I just wanted to say that we're going to do some attacks right now. So one more chance to change your name of your wireless device, of your Bluetooth device, before it comes up and is no longer anonymous. But our attacks will be passive in nature because of all of the troubles that we have with active attacks. If we wanted to do packet injection, for example, we'd have to calculate the channel map size, which can change as well over the 16,000, I'm sorry, is it 16,000? 1,600 times per second. There's some piconets that are AFH or adaptive frequency hopping, some aren't, which we have to identify at the pairing stage. And if we do transmit, we have to hit exactly the time sequence that device will transmit on. And some devices wait for 3 clock ticks, and some only 2. And we have to know when they're going to transmit and get that down to less than 10 milliseconds of the correct sequence. So if we wanted to just transmit at every single clock tick, we could probably do a DOS, or a denial of service or something like that, but it would be a really sloppy attack, which would be easy to detect. So other things which make it even worse is we have to understand the CRC checksum, which is dependent on the key of each of the device, which is also only transmitted at pairing stage. There is something called the automatic retransmission request, which the master puts out, and we have to understand the algorithm for that, implement it correctly, and be able to capture and decode those requests when they come from the master. Packet whitening is a form of scrambling the data, which is not used for security, but for leveling the radio spectrum over the time of the different clock sequences with the packets being sent out. Then we have roll switches, sniff, hold, and park mode, and all kinds of stuff that are in the standard, which are almost impossible to understand. So we're not going to do any active attacks. The Ubertooth 1 device, which I'm going to plug in now, actually can't do those by default. The libraries don't support them. Yes and no. I mean, there are some research possibilities into man-in-the-middle attacks, but for the most part, active attacks are kind of off the table. If you did have them, you could do all of these cool things. You could do packet injection, evil twin, passive analysis. This is kind of what we're going to do. It's a passive attacks. So let's try it. So, just back here. Let's see how far we get. So this doesn't fall down. Okay, it's plugged in. And what I want to do is maybe we'll start here. I think there's a nice screen full of samples. So this is actually not depending on the libraries of Ubuntu. This is part of Blues, which is part of the Linux distribution. I think I can make this bigger as well. That's big enough for me. All right. So here's a typical thing that anyone can do, even without a Bluetooth modem. It's basically scanning. In fact, I think it's using the HD0, which is the internal Bluetooth circuit of the laptop right now. What we found, probably because of proximity, is the node device, which is turned on, and that's its encoded Bluetooth device identifier, which unfortunately sometimes, right now it's in host byte order, and if you look at other tools, they will re-encode it in Bluetooth byte order, which is more like network byte order. So that's the first thing that we just discovered. And by the way, that thing is not discoverable. I'll show you that you can't see that. So this is in German, but what we're basically seeing here is that it's looking for devices, and it won't find it with the notebook's Bluetooth stack because it is in non-discoverable mode. So much for that. We did find it with the command line. The next thing we can do is an inquiry. And I believe that the Node Plus will not respond to this because they want to lock down their API. And okay, it did find it with its clock offset and its class. So we got one step further. We can try to get more information using classify and giving it the class name. Let's do that. This usually doesn't work, right? And here we see that the class name that variable as a manufacturer is given to their products is not an audio profile. It doesn't associate with a serial port profile. It's basically generic. And it's also reserved. So this is why devices that should be able to see it can't see it. And this is how they lock down their API. It's called security by exactly obscurity. Okay, so in any case, let's move down one more step. It's a first-class device. I'm not trying to say anything. It's just that. There's a few things. So let's try this. Let's obscurity doesn't take care of. So now we're trying to drill down. Couldn't do it. Let's get the records out. All of these commands are on your Linux computer because they are part of the Blues project. So that's the Bluetooth device ID for the Node Plus, and it's already giving us even more information like service name, handle. It's telling us that it's accessible via SPP, or the serial port profile, the Bluetooth 1 and Bluetooth 2 specifications. It has descriptors for these with these portions of the stack, RF-COM, a whole bunch of stuff from a non-discoverable device. Records, so then, okay, so let's move on to the next one, and these are, next slide. Okay, so now we're actually starting to get down to business with the Ubertooth libraries, which only work if you have an Ubertooth device plugged in. They're actually not very expensive, they're $100. So let's see, okay, here is the spectrum of this room right now. What do you think about that? So, what are we looking at? This is actually mostly Wi-Fi, I assume, because it's the same spectrum, right? There's not too much Zigbee and less the lights, like Aaron talked about. If he's right about the lights, it could be one of these bands. This is the first band of Wi-Fi there. This is the 11th band, or close to 11th, probably where it falls off, because there are a few others before we hit 2.5 gigahertz. And then somewhere along there, it could be anywhere as Bluetooth because of the channel hopping. We have 79 channels of Bluetooth. So that's always pretty cool. Dominic still did a great job with his software. Let's do a command line scan. Now we're going to be looking for non-detectable devices as well as detectable devices. And I wouldn't be surprised if there's more than one device in this case. So anything with a unique LAP will be a different device. Well, so it looks like everyone's turned off their Bluetooth, or you're out of range. Bluetooth is only good up to 10 meters, so about half of the room is out of range. And the first 10 meters is either conflicting with another radio signal or something like that. That's not too good. I've never seen this before.
Nice.
Should we call Dominic? Hey, Dominic, what's going on? So I think, okay, I'm just going to Control-C out there. Typically, at the end, it is able to decode the clock, the internal clock sequence, which is necessary. But in terms of time, I think this is a good one as well. We'll just move on. So here we're receiving the frames from any device. What we'll do now is, for example, pair this. So I guess I can't show you the screen at the same time as we're decoding. But I will connect the device. I think it beeps or something like that. Yep. So it's now paired, although it's non-discoverable, and it's paired only because of the API that's closed off. I'm using that official API to create this program. So that's why it worked. You can pulse the LEDs, push them there, turn them off again. And all of this is going over Bluetooth, so it's showing up in our RX, our receive. Push the button. Okay, so what we can do now, for example, we can measure the temperature of the room. Right, instead of an RX, which is what, oh. My guess is that it's possible that if I did and I forgot to unplug and plug it back in, that's the best way to reset it. I'm not sure about that. Okay, we got out of there. And the next thing to try, I won't do this dump because it just dumps raw bit data. So you need to dump that to a file or something like that. And what we can do here, but we need to use the correct LAP value. There it is. probably the one that's most common. I actually recognize it because it doesn't change the device. So let's use that. And the UAP will need that as well. There it is, UAP 39 found after 51 packets, so we'll put that here. And A at the very end just says to decode, keeping in mind that it's using Bluetooth 2 or Bluetooth. The second specification mandates adaptive frame frequency hopping, so that's what the A stands for. So let's go back and turn this back on, and then we'll use this follow command, which basically gives us the data from the bodies of the frames as well. The command that we used before, which is this RX, just gave us identifiers without any data. So as soon as I can turn this on, then we'll use it to measure the temperature of the room and get the data from that. So these are all passive attacks, which partially succeed. Because it actually drops quite a lot of frames. It's not 100% accurate with this frame hopping. I have to restart this application as well. So now we're back in business, we're connected. Therma has been detected, no plus is ready to use. Stream Therma. Whoopee, you guys see that? Okay, so we're measuring about 22 degrees. It shows on the screen, which you unfortunately can't see. And there's an AFH map, which it decoded pretty soon, pretty fast. That was an adaptive frequency hopping map. And we're getting a lot of null and pull. I guess I can use that as a laser pointer, can't I? So we're getting a lot. Hey, check that out. A double layer laser pointer. I love this. Pull and null frames contain no data. This is kind of a Bluetooth device way of saying it's still here. It's a keep alive for the master so that it doesn't drop the connection. And what we're waiting for, more data please, more temperature differences. Where is it? Where is it? Okay, it's only good for 4 meters. So we're waiting for, that it's going by too fast, but I'm pretty sure that we're capturing data now. Waiting for a variety of DM1 frames or anything with data. Where can it be? That would be really cool to show a data frame. Maybe we have to wait some more. Okay, how about if we turn the laser off and we start scanning some barcodes? So I got my airplane, luggage ticket, and I'm just going to scan that barcode. Scanner. So I just scanned that barcode for my inbound, scanned that one for, okay, that one. Here's a SDHC card with a nice barcode on there, scan. All right, so failed to decode packet, but I'm sure that we got something. So let's search for DM1. That's something that we see pretty often. It's not there. Oh, there. Okay, so we did find some data. So do you guys see that? Payload length, 13 bytes, and then the decoded data frame here. So that's probably, I don't know, a barcode or an encoded temperature value, right? And I don't know what DM stands for. There is about 5 types that I've seen. But these are, and then we have a bunch of keep alives, and that's basically capturing Bluetooth data. And we use the follow command for that. These are other things. Most of them are DM1 and right. So let's go to the next one. BLE recon looks like this. I don't think we have time, but this is what would happen if we attacked my wristwatch. Very similar. The data packets look similar. The protocol is actually different. If you want to try some of these things and you have a device that has a closed API, for example, like this Node Plus, what you can do is, for example, if you have an Android device, you can root it, or I don't even think, yeah, you do need to root it to get the log file out, but you can just select this, you can't see that too well. What it says is enable Bluetooth HCI snoop log, and that will write to etc Bluetooth BT stackconf. I'm sorry, that's what configures this capturing, and then it writes to /SD card BT data, something like that. In fact, I have it here. I have a copy of this, and it looks like this. We can do a Wireshark quickly. BT snoop is the name of the file that I captured before. Measuring this watch, we're at 54 minutes. This is kind of what it looks like. You get quite a lot of stuff, and you get the data as well, I think. You see that? So that's the poor man's way of capturing data, even from devices which provide closed APIs. So there's a lot of ways to attack Bluetooth devices, even the non-discoverable ones, even the ones with the closed APIs. And we want to do this for defensive measures, of course, and for having fun, and for whatever else. So there's, just in case for people who like reading some resources, this is kind of a book not geared toward hackers specifically, but kind of a industrial thing about healthcare, if you work in a hospital or you want to help improve medication systems or airlines, and things like industrial. A lot of, I think there's good weather application in there as well. Now, what I'd like to do in another day, in another life, I think, because there's so many sensor telemetry protocols popping up all over the place, like Zigbee is a really exciting one. These are the kind of the next steps in the research. Some more active attacks as well. I think Dominic has his hands full with a lot of other things, so we don't have time for a short film clip. So this is actually what we talked about. There are business cards up here if you don't have time to ask a question, or if you don't want to ask a question in public, you can get a business card and contact me privately via email. There's business cards as well from the representative from Variable, who provided us with this device for testing. If you want to grab one of those. Unfortunately, we didn't get around to doing a lot of testing with MQTT, but that could come in the next year, right? So that's all we have for today. Thanks for coming to the Sensory Telemetry IoT presentation.